In many cases, the solar collectors are connected to heat exchangers, especially if you are using some sort of ethylene glycol as the heat transfer fluid that would pass through the heat exchanger, so that you would avoid, for example, the occurrence of corrosion. If you used raw water, you might use additives to avoid corrosion, so that you would not like the water passing through the solar collector to come into your system. Suppose that you are using it for taking a bath or for cleaning or whatever. You don't want this water to be mixed with any chemicals. So to separate that, we make whatever is going to pass by the solar collector is in a closed loop. It will be heated, and the heat is transferred to your water, be it raw water or sweet water or whatever, through a heat exchanger. So we will see, as I just stated, that we are going to deal with heat exchangers in some of our applications where the solar collector systems are being under study. So it is worth then to consider a quick reminder of heat exchangers. There is something in the book that would, in section 317, talking about the heat exchangers, but I would just rather remind you in some sort of a nutshell that goes a little bit beyond what's been mentioned. For heat exchangers, the kind of analysis we normally do is classified into, so if I say that we have heat exchangers analysis, that can be either rating or design. By rating, I mean that what we want is the outlet temperature and heat transfer rate. Whereas for design, we have all the temperatures, we have the heat transfer rate, but what we are looking for is surface area of the tubes. So these are the two basic classifications of heat exchanger analysis. Sometimes we can refer to, I wouldn't call it a third classification, but sometimes we tend, let me admit, there's somebody I think is waiting. Yeah, in some cases we tend to do testing of a heat exchanger. And by testing here, I mean, we need to see what has changed in the overall heat transfer coefficient value. It may change with time. Who may know why? Why would the heat transfer coefficient change while you are using a heat exchanger with time?
One reason is fouling.
Exactly. When fouling is there, fouling usually is a function of time. As the time passes, the fouling factor increases. And actually there are models that talks about how the fouling factor increases with time. Some models are saying it is increasing linearly with the number of months. Others would say, no, it is increasing asymptotically. And by the word asymptotically, I mean that it would start, for example, at a small value, and then with time, with months, it keeps on increasing at a certain rate until it reaches an asymptote, like a constant value. So as if this is the fouling factor, and here this is the time in months. So that would be different ideas. Why would we refer to what we call testing for the determination of the heat transfer coefficient? But the major two ways that would analyze the heat exchanger analysis is basically through rating and design. As a matter of fact, Rating is one way that we know the performance has changed, and so we do testing to see how much is the overall heat transfer coefficient right now. And that's why in the design of heat exchangers, in many cases, the designers go for typical values of the fouling factor. For example, it is expected that with this quality of water, the heat exchanger will foul in, say, 12 months. So they take this fouling factor into consideration and they increase the area a little bit more than the needed area, so that you'll find that the heat exchanger, when it is new, it is overperforming, so that eventually, as the time passes, its performance matches the design condition. Now, when we are talking about rating, rating is basically what we call to as performance analysis. In rating, the kind of information that we have the flow rate of the hot fluid and the cold fluid. So these are two values that we know, m dot hot, m dot cold. And since we know the fluids, so the specific heat is known as well. M dot into, m dot cold into Cp cold, we call it the specific heat or the capacity rate cold. And then m dot hot and Cp hot multiplied by each other is nothing but C hot. What we do here is we try to look for the minimum value. What is the minimum value of in between C hot and C cold? Our minimum value here is going to be our reference fluid. The fluid that has C min is reference fluid. In heat exchangers rating, the area is known. And accordingly, we can calculate also what we refer to as Qmax, which is C minimum into delta T max. Delta T max is the hot fluid temperature N minus the cold fluid temperature N. This is the maximum temperature difference within a heat exchanger. A heat exchanger would have one fluid that is entering, the hot fluid entering at high temperature, and due to transfer of heat to the cold fluid, its temperature drops. So this is TH, inlet and outlet. Suppose I'm talking about a counterflow heat exchanger. The cold temperature enters at a low temperature, and its temperature increases because it is receiving heat from the hot fluid. So that the highest temperature within the heat exchanger is T hot N, the lowest temperature is T cold N. That's why when I'm saying T hot N minus T cold N, this would be considered as the maximum temperature difference. Can a heat exchanger operate with a temperature difference of T hot N minus T cold N? No, it's the theoretical maximum. This is the ceiling that we cannot exceed, and that's why we are taking it as a reference. For rating, as I mentioned above, what we are looking for is what is the actual heat transfer for that existing heat exchanger, and what is the outlet temperatures. Normally, you know the inlet temperatures. You have a temperature of oil, which is coming at, say, 100 degrees centigrade, and you need to cool it down by water at 25. So the hot temperature is known, the cold temperature is known. And then you need to see when you apply a heat exchanger with a certain area, and it has a certain overall heat transfer coefficient, then what will be their heat transfer rate and what will be the outlet temperatures, hot and cold. In order to do rating, what you need is to apply a method which is epsilon NTU method. Epsilon is what we refer to as effectiveness, and the NTU is the number of transfer units. So this is basically the effectiveness number of transfer units method. What do we have here in this method? We have basically the effectiveness value is given in tables or charts. We have the effectiveness as a function of the ratio, which is basically C minimum over C maximum. We have both C minimum and C maximum. As I mentioned, we calculate C hot, C cold. We see the lower value is our C minimum, the higher value is our C maximum. So epsilon is given as a function of C minimum over C maximum and number of transfer units. What is the number of transfer units? It is basically the overall heat transfer coefficient for the heat exchanger into the surface area divided by C minimum.
Doctor,
Yes.
the effectiveness is always less than 1.
Yes, I'm going to talk about the definition of the effectiveness now.
Okay.
So effectiveness is obtained from tables or charts as a function of C minimum over C maximum and the number of transfer unit, depending on the type of heat exchanger. So you are going to have a table, or usually have a table of effectiveness, and the effectiveness is given as a function for a double pipe heat exchanger, parallel flow, double pipe heat exchanger, counter flow, shell and tube heat exchanger, whether it is 1, 2, 1, 4, 1, 8, 2, 4. And by these numbers, I mean how many shells and how many tube passes. For example, a heat exchanger with one shell and 2 tube passes would be looking like this. So the tubes are going into a pass and then another pass. This is what we call 1-2 shell and tube heat exchanger. So depending, or a cross flow heat exchangers like the radiator. So depending on the type of heat exchanger, you are going to write or to select the correct formula for epsilon. What is epsilon? After you calculate epsilon, what does it represent? It represents Q over Q maximum. And this is the answer to your question. Q maximum is the ceiling that we can never reach. Accordingly, epsilon should always be less than 1. You can never have a way or have a case where epsilon exceeds 1. Or even equal to 1, because you are not going to reach for Q maximum.
Doctor, then why don't we call it like efficiency? Because effectiveness is like when we see fins, when we see the effectiveness of fins, we can exceed 1.
Fins
I don't
is
know.
the
I think
only,
efficiency is
yeah,
better.
fins is the only kind of application where it would exceed 1. But you can hardly find, I mean, we are going to talk about the word efficiency, the word effectiveness. The word effectiveness is coming from how effective this heat exchanger is in transferring the energy. So this is some sort of the origin of the word, how did it start it. But it is the common expression for the heat exchanger to call it effectiveness. And yeah, it's probably this is your last courses. If you happen to have a course of related to the mass transfer, then you have like combined heat and mass transfer devices like a cooling tower. Again, we use the effectiveness as a way to represent the performance of the components. It's like how effective it is in doing its business or doing what the function it has been made for. Q, or the heat transfer rate, is basically C cold, T cold out minus T cold in, and it is also C hot, T hot in minus T hot out. So what we see here in this slide is a summary of what we do for rating a heat exchanger. Rating, again, is performance evaluations where we know the flow rates, specific heat area, overall heat transfer coefficient, and we are looking for the outlet temperatures and Q. If you know the effectiveness from the correlations, and you know the Q maximum by definition, then you can get Q. Once you get Q, and you know the value of C, and you know the inlet temperatures, then you can determine the outlet temperatures. So that's for rating. If I'm going to talk about heat exchanger design, the situation is slightly different. And for design, I would clear the slide. If somebody has a question, it will be fine. Otherwise, we'll move to the next slide. Okay, so for the next slide, here basically I'm going to talk briefly about heat exchanger design. And by design here, actually, from people like us working in the thermal area, we call it thermal design, which means that I'm not calculating the stresses of the tubes and how the tubes are installed and welded and what should be the thickness of the heat exchanger shell. No, I'm not looking at that. But by thermal design, I'm only looking for how much should be the surface area for our heat exchanger. So I'm talking about that I need to design a heat exchanger that would heat a certain fluid with a mass flow rate. I would heat it, for example, from T cold in to T cold out. In order to do that, I'm using a hot fluid with a certain temperature T hot in. Or I need to cool down a fluid from T hot in to T hot out, and then I'm using cold fluid of T cold in. So we know at least three temperatures here. Actually, knowing three temperatures means that you have them all, because Q is m dot cold, Cp cold, T cold out minus T cold in. It is also m dot hot, Cp hot, T hot in, T hot in minus T hot out. So if you know three temperatures, you can get the four. We know the overall heat transfer coefficient, or you can get it. If you know the flow rates, then you can calculate the Reynolds number, you can get the Nusselt number, you can get the value of H, and then you can calculate the overall heat transfer coefficient. Maybe you may consider the fouling factor as well. And what we are looking for here is the surface area. To do that, there are basically a couple of methods that are being used in the literature for doing heat exchanger design. One old typical method is what we call the log mean temperature difference method, which states that the heat transfer rate for the heat exchanger is equal to overall heat transfer coefficient into the surface area into the log mean temperature difference into a temperature correction factor F. The temperature correction factor is given in tables or charts as a function of the effectiveness and the capacity ratio, which is C maximum, C minimum over C max. This is given in tables or charts. For double pipe heat exchangers, the value of the factor is 1. Otherwise, it is dependent on this value. So, do I know the value of Q? Yes, we can get it from here. Do I know the value of Q maximum? Yes, Q maximum is C minimum into T hot N minus T cold N. And the effectiveness is Q over Q max. So the value of effectiveness is a value that I know. And the capacity ratio is basically looking at C cold, C hot, and writing C minimum over C maximum. So these two values are known. And then I would go to the charts or tables and calculate the value of F. The log mean temperature difference is basically, if I'm going to consider that I have this kind of arrangement in a heat exchanger, where this is T hot in, T hot out, T cold in, T cold out, then we have, let's call delta T1, T hot in minus T cold out. And delta T2 as T hot out minus T cold in, then the log mean temperature difference is delta T1 minus delta T2 divided by the natural logarithm of delta T1 over delta T2. All temperatures are known, remember, in this design problem. I know them all. So I can calculate the log mean temperature difference. I can calculate the overall heat transfer coefficient. I know the value of Q. I get the F from charts or table, or for double pipe heat exchanger is equal to 1. So the only unknown here becomes the surface area. And this is typically what we do. Or there's another method, a modified method that you have taken in heat transfer that we refer to this method as the number of transfer unit method. It is like a shortcut of that LMTD method. The number of transfer unit method is a method through which the number of transfer units, the NTU, would be given as a function of epsilon and that capacity ratio. So NTU itself is given as a function of effectiveness and C minimum over C maximum. By the way, the C minimum over C maximum is what we refer to as capacitance ratio, CR. I know m dot Cp for the hot fluid, m dot Cp for the cold fluid. I select the lower one as C minimum, the other one becomes our C max. And then once I know this, once I know the value of the effectiveness, then I can go for correlations, again, equations that are tabulated that provides us with expressions of the number of transfer units as a function of these for different types of heat exchangers. So I'm going to select it based on whether it is a concentric tube heat exchanger, like a double pipe heat exchanger, parallel flow, counter flow, a shell and tube heat exchanger, or a cross flow heat exchanger. Depending on the type, I select the formula for the number of transfer units. Once I know the number of transfer units, I'm going to write its definition: overall heat transfer coefficient, surface area over C minimum. I know the C minimum, I know the overall heat transfer coefficient, so I calculate the surface area. So either one of these two methods, they are not actually two methods, it's one method, and this is some sort of a branch out of that method. Anyway, you can use either one of them for a design of a heat exchanger. So please refer to your chapter at section 317. It might be given an example on rating of heat exchangers. Just go through it. It will just cover, or it will be an application to the first part of what we discussed today, which is rating of heat exchangers. Again, rating is performance analysis where you have an existing heat exchanger, you know its surface area, but you need to predict how good it will operate, what is going to be the heat transfer rate, Q, which is sometimes called heat duty of the heat exchanger. So Q is called heat transfer rate, or sometimes it is referred to as heat duty of a heat exchanger, which means how much heat transfer it's able to transfer, or how much heat it's able to transfer from the hot fluid to the cold fluid. Any questions?
Doctor,
Yes.
do we need constant pumping for the hot and cold fluid, or
Yes,
concentric, or any type of?
definitely we need. This is always you are going to need, except for a specific type of solar collectors, which is called thermosiphon solar collectors. The thermosiphon solar collectors, we have convection and we have motion of the fluid, but the motion is only due to natural convection. Like hot water, water when it's heated, its density decreases a little bit, so it starts to move up and replaced by cold water down. So you have a natural circulation of water, which is normally slow, and the heat transfer coefficient is more. But sometimes people tend to use it just to save the use of pumps. But otherwise, especially with heat exchangers that you have tubes that the fluid has to pass through, then there is friction. Friction means we are talking about major losses. there is bends, there are valves, so there are minor losses. So you need to overcome the losses, and sometimes natural convection is not enough alone to overcome these losses, and you need to circulate the fluid by a pump. So pumps needed? Yes, definitely they will be needed in most of the applications to make the fluids move. And accordingly, heat transfer by convection takes place.
Doctor, how much flow rate, for example? How can I determine the flow rate?
It depends on your application. What is the heat transfer rate that you want? Suppose that, look at the equation that we have here for Q. I need to transfer a certain amount of heat here in a heat exchanger. The heat transfer rate is the flow rate into Cp into the temperature difference. Now, Cp is almost a constant, especially for liquids, which means here that based on the fluid that you have, I have a fluid at a temperature of, say, 100 degrees centigrade. I need to cool it down to 40. And now it's a matter of a trade-off. The fluid that I'm using for cooling it, what its temperature. If the temperature difference is small, then you need to have the flow rate of the fluid higher so that you can compensate for the temperature difference. If the temperature difference is large, you may need to reduce the flow rate. So there's no magic number for the flow rate. How much should it be? It depends on what kind of application. And as a matter of fact, based on that, you are going to make selection of the pump. What should be the flow rate? It depends on your conditions, how hot the fluid that you have, and how cold is the coolant that you have, so that you can effectively reach for a desired condition. The desired condition could be for cooling the fluid from this temperature to that temperature, or for heating a fluid from TC in to TC out, and this is your hot source that you need to heat it up. So now it depends basically on your specific case to determine what should be the mass flow rate to provide the required quantity or the required rate of heat that is going to achieve a certain temperature. So again, it's not a magic number. It depends on what is the fluids that you have, what are the temperatures, and then you can decide it.
Nice, Doctor. About the fluids, what type of fluids do we use? Do we use just water, or there are special?
Water and air are the cheapest and are the mostly abundant fluids. But sometimes, suppose that you need to have a solar collector system, and you need to install it in Tabuk this week. You cannot put water in the heat exchanger system. I mean, you cannot put water in the solar collector, because if the temperature went below freezing, water will freeze in the tubes. So it's not an option there. I can do it here in Dhahran. I can do it in Riyadh because it hardly reaches freezing temperature. But for areas where you can expect the temperature to go below, then you may use the coolant, which is similar to what you have in your car, ethylene glycol solution. So you use an ethylene glycol solution. Why? Because its freezing temperature is much less below than zero. Maybe it's minus 27, minus 30, or whatever. So even when it snows, when it is freezing, it still remains as a liquid. So it still circulates in the pipes. So water and air, they would be our best choice because you are not paying much for them. Air is freely, definitely, but we know with air, it has a lower heat transfer coefficient compared to water. So the size of the unit is going to be bigger if you use air. But water is a very good option. It's available. Raw water is not costly, so you can use it as your fluid. Theoretically speaking, you can use any fluid. But again, what is going to control us is the economics, the cost. Maybe one of the examples we used to give for that is when you are talking about heat exchangers or in heat transfer generally by conduction. It might, the radiators used to be made of copper before, but copper was expensive. Yes, but its thermal conductivity is 486 watt per meter Kelvin. What about silver? Silver has a thermal conductivity much higher than copper. Why don't we make our heat exchangers out of silver?
Very expensive.
Exactly, that's the point. So although it may perform better, so what will be controlled here with is the economics, how much we are going to pay to get our job done. So you are actually, they are not even using copper now for many of the heat exchangers. They moved into aluminum, and now they are going into some sort of a metallic alloys that would guarantee relatively high thermal conductivity, K, and they are cheap. In water desalination systems, you have like the multi-stage flash desalination systems that you can see them if you're driving across to the SWCC in Azizia or in Jubail, you'll find that you have units there. The units are, each one of them is made of something like 22 units or 22 stages. The early stages are experiencing salty water and high temperature. High temperature, I mean something closer to 120. Then what kind of materials used to be there? Previously, they used to use like an alloy of copper nickel. You cannot use copper alone because the seawater is aggressive to the copper. So use an alloy, copper nickel, and then it becomes copper nickel 3070, which means that 30% nickel for the high temperature application and 1090 for the lower temperature stages. And then they started using the duplex stainless steel, which is stainless steel cover from both sides of the tubes. It is expensive. And then they had to use titanium for the high temperature applications, especially that with time and advancement in the knowledge, they tend to increase the temperature of the seawater that they heat. So titanium becomes a very good choice. Titanium has problems. Number one, it's very expensive. Number two, its thermal conductivity is less than that for aluminum. So they used to use like thin tubes of titanium, and they use it only for the first few stages, and then the rest of stages can be made of copper nickel. So the point here is it's a trade-off between the cost that you have to pay and the function that you need to achieve. I hope I did answer your question.
Thank you, Doctor.
Okay, if no further questions, then we can move on. So that was just like a brief going into or some sort of a reminder of heat exchanger analysis. What we need to get into now is to continue to or move on to chapter 4, which is talking about radiation properties of opaque surfaces. And it's not the first time to hear about opaque surfaces. You have been introduced to that in your heat transfer course in the radiation part. And that time we said that most of the materials we are dealing with are opaque, except for glass or glazing. This is basically transparent. Otherwise, it is basically opaque surfaces that we are dealing with. So in this regard, we are going to talk about in this chapter about basically the properties of opaque surfaces. So let me share this slide with you. I don't think you can see it. Oh, yes. So I'm gonna try again, and yes, get the big screen in. So it is radiation characteristics of opaque materials. We are supposed to be covering this chapter in a couple of classes, this class and next class. And by the way, I think it is the next class that we agreed that we are going to have our second quiz, isn't it? Which will be related to the second homework. So today is Wednesday. On Monday, sorry, our class is going to have like a 20 minutes quiz related to the chapter 2 that you have already submitted the homework for. Now, in this chapter, we are going to look at a detailed, we are going to consider a detailed discussion of radiation characteristics of opaque surfaces. Again, opaque, it means that the value of the transmissivity is 0. So what we have basically is absorptivity. The surface is going to absorb energy and it's going to reflect energy. So absorptivity and reflectivity, or absorptance and reflectivity, are the only functions that, or the only properties that do exist. But no transmissivity, as opaque surfaces do not transmit radiation through. For many solar energy calculations, two quantities are normally needed. The absorptance, which means that the ability of the surface to absorb energy and accordingly gets heated up because of the energy it absorbs. And the infrared emittance. You have a certain surface at a certain temperature, and we know that any surface above 0 Kelvin, above the absolute zero, the thermodynamic zero temperature, starts emitting radiation. So basically, absorptance and emittance are the basic two functions that we might be interested in. Definitely, we'll be talking about reflectivity as well, because we will see how the reflectivity is crucial in the determination of these two properties, the absorptance and the emittance. The values of these quantities are available, but sometimes you don't find all the information that you want, which means that in some cases, you might not be able to determine these values. So we're going to be exposed to some sort of manipulation through which I can estimate the values of the absorptance or the reflectivity, the emissivity. And this is basically by knowing the value of rho, or the reflectivity, meaning that if I know the value of rho, I should be able to determine what is the value of alpha or what is the value of epsilon. So this is basically what the whole chapter is all about. Now, there's something here like sort of a getting used to the notations. You might have passed by quickly this concept in your introduction to radiation, but as I mentioned, because the heat transfer is some sort of a full course, it has so many materials, so sometimes when there's no time, or if you spend like extra time in conduction and convection, there will be very limited time to radiation, and then time would not be enough to get into this, or stress into these points, or that are related to these conceptual issues. The naming, that when you are talking about a certain name of a quantity, the name should indicate what does it mean. For example, if I'm saying something is monochromatic, it means that it is evaluated at a single value of the wavelength. Mono is one. So monochromatic, it means a single wavelength at one value of the wavelength. So look at this first expression that we are going to talk about. Monochromatic directional absorptance. We know the absorptance is alpha, which is the ratio of the amount of energy absorbed with respect to the amount of energy incident or falling into the surface. How much did we absorb out of the surface? For example, if a flux of 900 or say 10,000 watt per meter square, and the surface has absorbed 400, so the absorptivity is 40% or 0.4. So it's basically, this is what is it. But when we are talking about a monochromatic directional absorptance, the word directional, it means that it depends on the direction. So it depends on the angle. What kind of angles that we are talking about? We have basically two angles to worry about. The zenith angle, theta, but we don't say theta because most of the applications that we are dealing with, most of the formulations that we have, it has the word cosine theta, or it has basically the component cosine theta. So we're not going to talk about theta, we're going to talk about directly cosine theta. And cosine theta here is being termed as mu. So when we say alpha is a function of mu, then it means that alpha is a function of cosine theta, or indirectly alpha, it depends on the value of theta. But here, just for the sake of practicality, we're going to say it's mu, and mu is cosine theta. And the azimuthal angle. And note that the azimuthal angle here in this part of the course is called phi. So when we are talking about monochromatic directional absorptance, it means we are talking about absorptance, which is alpha. Monochromatic at a certain wavelength, directional, so it depends on both mu and phi. But when we say directional absorptance, I did not say monochromatic, I just said directional absorptance, which means that as if it has been integrated over the whole wavelength range. So it's a value that represents the absorptance for the whole wavelength spectrum that we're dealing with. That was monochromatic, so it depends on lambda. That was directional absorptance, it depends on the directions. So directions mean mu and phi, but the wavelength has not been mentioned. So it's a total value, it includes all the wavelengths. It's not only that, but we'll be dealing with monochromatic hemispherical absorptance. Hemispherical absorptance here, the word hemispherical, it means that it has been integrated over the two angles. So it does not depend anymore on mu or phi. It's talking about some sort of homogeneous expression over the whole hemisphere or upper half sphere here, as you can see it. So it has been like integrated over the whole theta, or actually mu, which is cosine theta, and phi. So it has covered all the surface then. So there is monochromatic, it depends on the wavelength. There is directional, it depends on mu and phi. And there is hemispherical, where it does not depend on the direction, but it can be monochromatic or it can be a total. It depends. So from here, when you get the word that we are evaluating monochromatic directional absorptance or monochromatic directional reflection or monochromatic whatever, you know that monochromatic means single wavelength, directional means its dependence on mu and phi is considered. Hemispherical, it means that it is not directional. And when we say absorptance or reflectance or whatever, and we did not talk about the wavelength, so it's been taught for the whole range of the wavelength. Now, in this slide, we are looking at the monochromatic directional absorptance, which is a property of a surface defined as a fraction of the energy absorbed from or with respect to the energy incident onto it. Monochromatic, again, so it's at a certain wavelength. Directional, again, that it is a function of mu and phi. And the defining relation is given here. So alpha, absorptance, which normally this absorptance, emittance, or reflectance, they are always fractions. So they are always less than 1. It's a ratio. And here it's a ratio between how much of the incident energy could the surface absorb, because part of the energy is absorbed and the rest is going to be reflected. So, and the subscripts that we have here in the numerator, we have the subscript A, it means absorbed. And in the denominator, we have the subscript I, which means incident. And normally the incident energy is high. Only part of it is bigger. Part of the incident energy is absorbed and the rest is reflected. Then we're talking about monochromatic directional emittance of a surface is the ratio of the monochromatic intensity. Now I'm talking about emissivity here. Intensity emitted by a surface to the monochromatic emissivity or the monochromatic emitted power of a black body. Epsilon is a fraction for a real body, but for a black body, epsilon is equal to 1. Emissivity is basically a ratio between the emitted energy of a surface compared to the emitted energy of an ideal emitter, which is the black body. And that's why the definition is given here. It is basically I lambda, so it's a monochromatic, it depends on the wavelength, it is directional, and it is compared to the black body. The black body is not directional. Black body is a total kind of of intensity, which is ideal in this case. The definitions that we are writing now, they can be written as monochromatic or total. They can be written as directional or hemispherical. So now it depends on what is the range that we are considering. And remember, now we're talking only about definitions. So we're defining these parameters just for our use. When we are talking about the hemispherical absorptance, emittance, or absorptance or emittance or and emittance, I'm talking about hemispherical now. So it accounts for, I did not say monochromatic, I said the hemispherical absorptance. So it is the absorptance or the emittance, which is considering all the wavelength range, and it is covering all the angles. And that's why here it's been integrated. The outer integral here from 0 to infinity, this is the wavelength. So it's taken about the whole spectrum of the wavelength. And then the 0 to 2 pi is basically the phi, the azimuthal angle, which is over the 180 degree coverage. And then the cosine values is a sinusoidal function that ranges between 0 to 1. So here we have accounted for all the ranges of the wavelength, the phi, and the cosine theta. When you do that, you get a total value of alpha, which is for all the wavelengths and for all the directions. It's hemispherical. And the same thing here applies for the value of epsilon. You are going to integrate it here as epsilon into the incident or the black body emitted energy divided by integration of the black body emitted energy, which is given as EB. And the EB basically is nothing but, in Stefan Boltzmann law, the value of, sigma into temperature to the power 4. So this is what we do. And normally we're not going to do that. We're not going to do this kind of mathematical integrations in our analysis, but this is just to know how did it come from. If you need to get over the whole wavelength spectrum, you should integrate with respect to the wavelength. Over the whole azimuthal angle, you should integrate with respect to azimuthal angle. The whole zenith angle, you should integrate with respect to cosine theta. The red ones are surface properties, monochromatic absorptance, monochromatic emittance, emittance of the surface, monochromatic emissivity, and hemispherical emissivity. You've also probably have heard about Kirchhoff law. Kirchhoff law has some sort of a proof, which we're not going to cover here. It actually proves that the monochromatic absorptivity is equal to the monochromatic emissivity. There is a couple of ways to do this. If you go back to some of the heat transfer books, it will tell you that it's okay if this is a surface here, and this surface, or it's a cavity, it's closed from all directions, but has a small opening here. And there's a source of emitting radiation here. This source may have a ray that's going to enter here. When it enters the surface, it will be reflected like that, and then reflected here, and then reflected here, and then reflected here, which means that most of the cases, it will not leave the surface out. So the value of the emissivity here, or the emitted energy, has all been absorbed, even if this body is not a black body radiation. So that was a thought experiment to show that epsilon and alpha could be the same. Another thought experiment is given in your book, saying that if you have like a cavity here, and the cavity have two surfaces here of different radiation characteristics, and it's all in thermal equilibrium, it means that eventually the value of alpha absorbed, since we're talking about equilibrium, so the value of alpha absorbed by the surface is going to be in balance with the value of epsilon of the emissivity so that it remains at a constant temperature equilibrium. The same thing applies for all surfaces, and from which they came up with this kind of approximation for the values of alpha and epsilon. Now, we are talking about reflectivity now, reflectance of a surface. It's a surface which is looking like a mirror or a shiny surface, so that the energy falling on the surface is not used for heating the surface, but it's being reflected. And we are going to need this kind of property a lot when we are talking about parabolic trough collectors, for example, so that all your target for this kind of application is to have heating of a tube fluid. You have a fluid passing in the tube, and you need to heat it by solar energy. So to concentrate the solar energy, use a parabolic trough so that all the energy falling parallel into this parabolic surface is going to be reflected here at the focal point. So the property that we are interested in here for this parabolic surface is that it should have high ability to reflect most of the energy that falls into it. You don't need it to absorb energy. I'm not interested in heating this plate. This plate is not important to me. I don't need to heat it, but I need to heat this fluid here in this tube. So the kind of property that I need to be maximized here for this surface is the reflectivity. I don't want it to absorb any energy as much as I can, and definitely I don't want it to transmit the energy. That's why it's not made of glass or glazing. It is basically made of shiny surface so that it would reflect the maximum possible radiation into a certain focal point where I'm putting a tube. And this basically is applied for parabolic trough collectors, can be for paraboloids or solar dishes. It can be for Fresnel reflectors. So there are different applications of this, and they are all effective in terms of getting us tremendous increase in the heat transfer, that sometimes what you have here inside the tubes is heat transfer oil that can be heated to temperatures of 300 to 400 degrees centigrade, sometimes more. So you can use it to generate steam, and then you have a Rankine cycle, but without a boiler. A Rankine cycle where you can get a steam. The steam can expand in a turbine and give work, or just to have a work output. Then you have a condenser, you have a pump, but at the end, instead of the boiler, you have this tracking system for heating the water into steam. And the same thing for the large power plants where you have a tower and the tower is surrounded by mirrors. In 2019, the largest ever solar power plant has been erected in Morocco. And previously, maybe 10 to 15 years ago, there is another one in Australia. The one in Australia has the tower, and the tower was surrounded by 500,000 mirrors. So that all these mirrors are basically receiving the solar energy, and they are reflecting the energy on a certain point. And this point is where the water tank is placed, and this is where water boils and converts to steam. So we're talking about some sort of a property which is substantially utilized in many applications of the industry. Now, we are considering again the issue of spatial distribution of radiation that is reflected from a surface. And here we have a classification. The radiation which is reflected is either specular. Specular is the figure down there. You can have like a beam falling in at a certain angle, and it is being reflected at the same angle. Theta is the angle where it is falling in. It's falling in something like a pencil shape type of rays with a certain solid angle in, and it's being reflected in a similar manner. This is a purely specular surface. The surface has to be shiny, has to be very smooth, has no corrugations at all, and which needs a little bit of machining. and it needs precise machining. Otherwise, what you will get is a diffuse surface like that. Energy will fall in, and then it will be reflected in all directions equally or homogeneously, and that's the diffuse surface. Both of these, the specular surface and the diffuse surface, are idealizations. I mean, you can hardly get, it's not easy to get a pure specular surface. And in reality, surfaces are general like this, which means that they are not specular, but they are not actually diffuse in a way which is geometrically perfect like this. It's having something like that. So in reality, the surfaces are somewhere in between specular and diffuse. Sometimes you do special machining to have a specular surface, and sometimes you do your surface would be rough in a manner that makes the reflections as much as possible homogeneous, like what you see here.
Doctor,
Yes.
how much percentage can we reflect in practical situations?
You can reach for something like 90% or so for some surfaces. As there's no way surfaces have to be heated by having solar energy falling in. So absorptance is going to be there. The surfaces will absorb some energy. So what you are trying to do is just to make them as shiny as possible, and then you can get a value of the absorptance is about maybe 10% or so, and the rest will be reflected energy. We'll be seeing that maybe in some of our analysis and applications for during this chapter, even especially when we look at some of the examples.
Doctor,
Hmm.
can we make use of this heat from the plates?
It depends on your design of the system. The latest design that has been released of of the PV panels, which are, the PV panels are the panels that are converting the solar energy into electricity. And
Photovoltaic.
and major problem of these surfaces is that the PV panels efficiency gets less or gets lower with temperature. So we're talking about two conflicting things. I should use the higher the solar energy intensity, the higher the electric power that you get. But the higher the solar energy intensity, the hotter the surface gets. And then when the surface gets hotter, its efficiency decreases. So they started to come up lately with something that they call PVT panels. They have panels which are basically PV, and in the back of the panel, there are channels for water to pass. What does water do? It cools the panel, so the panel temperature does not exceed a certain value, so you keep its efficiency. Meanwhile, you are heating the water, because as the water absorbs the energy, it gets heated. So you are making benefit of both. And this hot water, you can use it either for domestic water heating, or in some cases, like some research that was released last year from KAUST, is that they are making use of this water to be, or this water is basically seawater, and they use it for desalination purpose. So the answer to your question, yes, we can make use of the heat, but that something has not then been done over quite a period of time until the development of these ideas came in, and they came up with the PVT collectors. These collectors are available in the market. They started to penetrate in the market, but not very widely used. Maybe you can hardly find it here in the market. What you will find in the market here, the companies or the shops that are selling PV panels, they are just having the regular type of PV panels. There have been research even in our university here for the last maybe 10 to 15 years, talking about the PV panels with different ways to cool it down, maybe by using water spraying or a jet of water or whatever, but it was not with the intention of making use of that hot water. This idea developed lately, something like maybe 3 to 4 years ago, and they came up with this idea of making use of both heat for water that cools the PV panels, so that you can have efficient PV panels and you make use of that hot water as a byproduct.
Doctor,
Yes.
now if I want to reflect this beam or this radiation into the tower, and they have some sort of heat recovery from the collector itself. Will the heat recovery that I take from heat that I have taken from the reflector affect the amount of radiation reflected into the tower itself? Did you get my idea?
No, no, no. It would not. I mean, for PV panels, it would affect the performance because it's a function of temperature. But for the surface, the reflectivity would not be affected by the temperature. Whether the surface is hot or cold, as long as it's a shiny surface, it would not, because the temperature variations are not great, by the way. I mean, when you heat it up, you heat it to something like 60 or 70 degrees centigrade. Which is not enough to affect the radiation properties of the surface. So the reflectivity, I wouldn't think that it would be affected by having the surface being at higher or lower temperature. Okay.
Okay, Doctor, thank you.
Now this is the formal mathematical definition of the reflectivity here. And you see here, we're talking about monochromatic directional reflectivity. It's not only a monochromatic directional, which is given by equation 431, but it depends on the angles of the incident energy and the angles of the reflected energy. Look at this. We have mu r, which is cosine theta r, phi r, which is the azimuthal angle r, and then the same angles for the incident energy. And it's again, it depends on the value of lambda. So it's a monochromatic value. So definition of monochromatic directional reflectance can be given by that expression that you see here. And again, there's something that has been mentioned here regarding these angles. You can look at the angles down there. In case of symmetry, then phi r is or phi I is 180 minus phi r. This similarity here. In this sense, the same thing applies here for the value of theta I and theta r. Now, this is one of the important outcomes that we have from this chapter. Before, it's been stated that, or at the beginning of the chapter, that you don't always have enough information which are related to the epsilon and alpha, but you may have this information in terms of the reflectance rho. So if I know the reflectance rho, I can determine what is the value of alpha and what is the value of epsilon. Remember, what you have covered in heat transfer when you studied the surface radiation properties, we said that at time is the irradiation or the energy flux falling into the surface. Part of it is absorbed, part of it is reflected, and part is transmitted, out of which we said that the summation of alpha plus rho plus tau is equal to 1. A special case is for opaque surface where tau is equal to 0. So for this case, alpha plus rho is equal to 1. But we know that alpha, according to the Kirchhoff law, is equal to the epsilon. So epsilon plus rho is equal to 1. Alpha plus rho is equal to 1. So to determine alpha or epsilon, it would be enough if you have enough information about rho. You can determine the value of the rho, out of which you can calculate epsilon and alpha, as you can see here. So this is basically the basic, this is the basic idea that we started to stress on when we started considering the introduction to this chapter, which means that the equations that we have studied before, talking about definitions, it can be applicable here again. Whatever we said about definition of epsilon or alpha can apply for rho, and then you can use this radiation property summation to get the missing information in case one is there. Why there would be a problem in the determination of some of these values? Suppose that I'm interested in the value of alpha for a surface. Alpha for a surface, it actually depends on what is your source. So I should have enough information on the source to determine how much energy I'm going to absorb, but not for epsilon. Epsilon depends on the temperature of the surface, regardless of what's surrounding it, which means that in some cases, you may be able to calculate epsilon rather than calculating alpha. And the same thing, rho, it might be related to the surface property. So I can calculate the value of rho, but not the value of alpha, because alpha, it requires knowledge of what is the source of energy, which is sending its electromagnetic waves to fall into the surface that we are studying. So when we are talking about the limitation that we have for the absorptance is that it can be found if the incident intensity is specified. So I should know what's the incident intensity so that I can get the value of alpha. But I would not need it if I need to get the value of epsilon, for example, or rho. The relationship between the reflectance and the absorbance can be considered as a conservation of energy. As I just mentioned, energy is falling, total energy falling into a surface. The surface is opaque, so nothing is being transmitted. So the energy in is going to be the incident energy. The energy out is going to be the reflected energy. And in addition to the amount of energy stored, which will be used by the system to heat up. So the incident monochromatic energy is either reflected or absorbed. As a matter of fact, it is both. Part of it is reflected and part is absorbed. And here we come to this relation that I just described in the previous slide. For opaque surfaces, tau is equal to 0. So on the monochromatic level, rho lambda plus alpha lambda is equal to 1, or rho lambda plus epsilon lambda is equal to 1, since alpha and epsilon are the same according to Kirchhoff law. Or if it's integrated over the entire wavelength, then rho plus alpha is equal to 1. Again, I should remind you of the title of that chapter, that it is properties of opaque surfaces. Opaque means that the value of the transmissivity, or tau, is equal to 0. So it does not contribute to this equation accordingly. This is some sort of a graphical representation of epsilon. Remember, in epsilon, we said that we are doing a comparison between the emitted energy of a real surface with the emitted energy of a blackboard. Of a black body surface, or of a black body. So look at this. This is spectrum, monochromatic spectrum, or energy, monochromatic energy falling into a surface as a function of the wavelength. And we've seen that it takes this shape. It means that the value changes with the wavelength depending on the temperature. You can see it here. This is for a black body, and this is for a real body. So when we are talking about the value of emittance, or the emissivity of this surface, then basically we are talking about the energy emitted from a real surface, which is this, divided by the energy emitted from a black body. Energy emitted from a real surface is this part, it's A. The corresponding energy emitted for a black body is B. So the value of epsilon here becomes the ratio of A over B, which is basically the one that you can see it as being given here in the red color. So the monochromatic value is A over B. If you need to get the total value, you need to integrate it over the entire range of the wavelengths. What's good for us in terms of analysis in the determination of epsilon, it is written here. Epsilon is not dependent on any external surface, an external factor. I don't need to know what are the characteristics of the surroundings in order to estimate the value of epsilon. Epsilon is a function of the surface itself, the surface ability to emit radiation. So that I don't need to know if this energy is coming from the sun or it's coming from whatever source, because it's not like absorptivity. Absorptivity, I should know what is the source which is emitting the radiation, so my surface is going to absorb how much of this. But here, it's only a function of the surface temperature. And definitely the wavelength becomes as a part here. This is here the issue of the absorptance. For the absorptance, I should be able to know how much is the incident spectrum. Is it being like shaded or not? I mean, it's some sort of information that, or additional information that I should know. But in terms of a comparison, if the upper curve is representing how much is the energy falling into a surface, part of this energy is absorbed. So the absorptivity or the absorptance again is given as C, the part of energy it has absorbed, divided by D, the part of energy or the rate of energy that has been incident into the surface. So this is some sort of a graphical representation of these properties, as you can see. So emittance is specified by nature of the surface, while the absorptance depends on external factor, which is what is the source of energy that is falling into the surface, and then the surface is going to absorb part of it. That's why it's probably easier to estimate the value of epsilon rather than getting the value of alpha, just because of that. Alpha, it needs extra information regarding the source. So the specification of alpha becomes meaningless until we know what is the source, what's the incident energy. It should be described to get that. However, just for simplification, in this course, we are interested in solar energy. So if we are going to talk about the value of alpha, then we are going to mean alpha, which is going to be absorbed out of the solar energy. So when we refer to the calculations of alpha, we are going to refer to it as either talking about a black body or talking about terrestrial solar spectrum, which is falling into the surface. And this terrestrial solar spectrum is being given in tables. In chapter 2, we have table 261, and this table is providing us with a realistic basic where you can calculate the value of alpha. Actually, it is given the fraction of energy as a function of the wavelength, and even the midpoint value of the wavelength that we can be using for estimating it. I think we are going to get into an example in a while, and that example we can do it as our first activity in our next class, inshallah. So I'm going to stop here, and then we are going to pick it up from here in our next class. Remember, inshallah, in our next class we are going to go through the example, we are going to complete the chapter, and we have a quiz which is related to homework number 2, inshallah. So thank you for paying attention, and we'll see you on Monday, inshallah.
Thank you very much, Dr. See you.
يعطيك العافية دكتور.
الله يعافيك، شكرا لك.